Okay, so let's continue our discussion on renormalization, and today I'm going to show you how to get rid of infinities that you get in Feynman diagrams. Okay, so let's quickly summarize what we have been doing so far. So we are interested in the 5-4 theory, whose action is the following, and this is in 4 dimensions. Okay, let me reduce a bit, brush palette. Yeah. Okay, and then as you know that because we have divergences, because our integrals were not defined in 4 dimensions, we decided to do analytic continuation. To d dimensions, which we are taking to be 4 minus 2 epsilon, okay, dimensions. So the action with which we will work is this 4 minus 2 epsilon, okay, and then we have half del mu phi minus half m square phi square minus lambda over 4 factorial mu to the 2 epsilon phi to the 4. Okay, and as you recall, the reason why we have mu to the 2 epsilon here is because the coupling constant becomes dimension full as you go to d dimensions. So in order to have the dimensionless coupling, I have pulled out a scale mu and I have raised to the power 2 epsilon. So mu is a fixed scale. You decide on a mu and then you proceed. Okay. Otherwise, you would have had lambda times mu epsilon as some, let's call lambda d, some d-dimensional, a coupling constant in d dimensions, which would be dimension full. So instead of working with lambda times mu epsilon, mu to the 2 epsilon, you could have worked directly with this, but this would have been then dimension full. Okay. So also you should note that you don't have 3 parameters, you have only 2 parameters, m and lambda. Mu you fix, right? That's not something, so because see, lambda d is 1 parameter, okay. Splitting that lambda d into 2 factors doesn't make 2 parameters. Okay, you cannot, if you could, then you could have also split into 10 other factors and said that you have 10 parameters, which makes no sense. So you really have 2 parameters, m and lambda, and clearly your results should not depend on the choice of mu. Okay, because you are going to vary only lambda. Okay. Another way also, when you go to epsilon going to 0 limit, there is no mu because this epsilon will drop out. This epsilon goes to 0 and this mu to the 2 epsilon will drop out. So in 4 dimensions, when you go back, again you see there is no mu. Okay. But we will see that even though results should not depend on mu, the physical observable should not depend on mu, but when we calculate, we are going to see dependence on mu. Okay, we'll make more remarks about that later, but this is something that is going to happen. Okay, and some notation now. These phi's, the fields that appear here, the field phi, the parameter m, and the parameter lambda, these are called Bayer parameters. or bare fields. So this one is a bare field. This is bare mass parameter, and this is bare coupling constant. Okay. Then we did the following. We wrote the same action as, so I am putting equal to, so it's the same as, it's not something different, as 4 minus 2 epsilon d to the 4 minus, okay, I forgot x here. Then we redefined fields. Okay, we said that, okay, the bare field is z phi to the half and then phi renormalized. Okay. And similarly, bare coupling, bare mass is Zm times m renormalized, and lambda, the bare coupling constant, is Z lambda times lambda renormalized. Okay, where the Z start at order 1. This is small z, lowercase z. Okay, and these zi's start at order lambda r. Okay, these fields phi, mr, and lambda r, we will keep them finite. Okay, that is something we demand, and you are going to see that the fields phi, m, and lambda will become infinite. Okay, and all that infinity will be contained in the z phi's, zm's, and z lambda. But let's anyway progress and see explicitly that this is what happens. So with these definitions, we wrote the same action. Okay, not changing the theory, it's the same theory. We wrote as half z phi del mu phi r del mu phi r minus half zm square z phi mr square phi r square. Okay, all I am doing is substituting these definitions in this section here. Okay, and that is what gives you this thing. And then minus lambda r over 4 factorial mu to the 2 epsilon, okay, z lambda z phi square phi r square. Okay, and then I added and subtracted the terms which you get in the action here. Okay, but phi and m and lambda replaced by phi r, mr, and lambda r. Okay, because this is these are the ones which were originally there, right? So I just want to have Feynman rules which are which the Feynman rules contain the set of Feynman rules which I already had. That is what I want to ensure. So I just add and subtract this term, okay, with the fields and parameters replaced by renormalized fields and renormalized parameters. So the same action I rewrote as d4 minus 2 epsilon x and half del mu phi r minus half mr square phi r square. Remember, mr has the mass dimension 1. Okay, so that is why there was no need of any additional mass scale. And then we had lambda r over 4 factorial mu to the 2 epsilon phi r to the 4. So I added this and then I subtracted and I get this plus, let me start from here, plus half z phi minus 1 del mu phi r minus half z phi zm square minus 1 mr square phi r square minus lambda r over 4 factorial mu to the 2 epsilon z lambda z phi square minus 1 phi r to the 4. Okay, it's again the same action as before, but written slightly differently. Okay, the first line, okay, that's what we had in the original action with the replacement of the fields and parameters. The second line is new, and these are called counter terms. Okay, so all the terms in here are called counter terms. Okay, remember I have not put any additional terms as you know. Okay, but still I am calling these as counter terms and this as the original thing because it looks like what you had originally, even though the fields have been rescaled and mass parameter and coupling constant has been rescaled. Okay, so that's just a way of saying that what we have here is counter term. Okay, and you will see what it is going to counter. Okay, so and then we had the Feynman rules, momentum space Feynman rules. So the propagator is I over p square minus mr square plus I epsilon, right? Because this is what is going to provide you with the propagator, and that is the mr here. So that is mr square plus I epsilon. Okay, then as earlier you have this vertex which gives you a factor of minus I lambda over 4 factorial. Okay, and then you have a 2-point vertex. Okay, and remember I called this is a vertex because z minus 1 is of order lambda r. Okay, so this term comes with the order lambda r, and this has two fields phi. Okay, so it will have two legs. So this vertex, just like this vertex has 4 legs because you have 4 fields here. Okay, if you go back and see how we derived Feynman rules, why this has 4 legs, you will see that for the same reason this has 2 legs. Okay, just a second. Okay, and this you should see that in the Fourier space, this will give you the following. The moment of space Feynman rule is the following. Okay, and we also had the vertex coming from this one. Okay, this has 4 legs, and this also starts at order lambda r, right? Because z lambda is of order 1. Z lambda is 1 plus order lambda. Z phi square is 1 plus order lambda. Okay, so when you subtract 1, it will give you a term which is of order lambda. Okay, the same is true for this one and this one. All these terms. So when I wrote this one, I have included both of these here. Okay, and now I am writing this one. Again, to remind that this is coming from a counter term, I have put this circle here, and the Feynman rule is the following. Okay, just like you had minus I lambda over 4 factorial here, you have the same thing here. Okay, I have missed a mu to the 2 epsilon. Mu to the 2 epsilon z lambda z phi square minus 1. Okay, so since this factor is of order lambda r, you already have an explicit factor of lambda r. This vertex or this term is of order lambda r square, and that is why this vertex is of order lambda r square. Okay, so it's one order higher compared to this vertex and this vertex. These are all of order lambda r. Okay, and remember, when we do perturbation theory, we have to do things order by order in the parameter lambda r, right? Because lambda r is our expansion parameter. Okay, we are organizing the perturbation theory using the parameter lambda r. Okay, so a term which is of order lambda r square, okay, is a higher order term compared to an order lambda r term. Okay, so if you want to get a result which is correct only up to order lambda r, you do not have to worry about terms that appear at order lambda r square. Okay, so as of now, I have not really done anything. I have just renamed things. Beyond that, I have not done anything. Okay, now let's go and try to calculate some physical thing in the theory. And in the same theory, there is nothing, it's not a new theory, it's the same theory. And let's try to figure out the physical mass. Okay, that's one thing one would like to know. What are the physical masses of the particles? Okay, and that is something I want to calculate. So what you should note is that I will choose some value of mr, some value of lambda r, some value of mu. Okay, these will be fixed, so they are inputs, okay, or choices. And then I ask, if I have made these choices, then what is the physical mass that I get? And of course, that physical mass will depend on these choices, right? Mr and lambda r. Let's see then how to get it and what we get. So okay, physical mass is something that you can observe, right, in an experiment. Like you can find out what is the mass of an electron, or what is the mass of any other particle. Recently, one of the fundamental particles which was discovered most recently is the Higgs boson. Okay, so what is the mass of the Higgs boson? That you find from experiment. Okay, if you are aware of the story of it, people were searching for a peak in the diboson, diphoton channel. Okay, because it's one of the easiest ways of finding it. So you look at two photons in the final state. Okay, the photons are usually denoted by curvy lines. Okay, and you have two protons colliding. So this is, I'm denoting proton. Okay, they collide at LHC. Okay, and then of course many processes happen, and you, let's say, are looking at a process in which you get two photons. Okay, and you construct the invariant mass of these photons. So if you have, this one has momentum p1 and this one has p2, then p1 plus p2 whole square, that is what is called as invariant mass. Okay, and people found a peak in that invariant mass, okay, at some energy. So from there you find out what is the Higgs mass. Okay, because this will give you the this is invariant mass squared. Okay, this has dimensions of energy squared or mass squared. So this is invariant mass squared, and from this you find out what is the mass of the Higgs boson. Okay, that is how it was done. Now that mass of the Higgs boson is something physical. Okay, irrespective of what theory you have, what r and lambda r, etc. you are choosing. Okay, it doesn't care about those things. It's an experimental outcome. So you find that. Now once you have found MP, okay, or some number of observables you have observed in the experiments, okay, then you can, using those values for the physical mass or whatever else you have calculated, okay, you can try to fit what mr and lambda r would be. Okay, so that is how you can determine the values of mr and lambda r. And then if you have a new observable for which you want a prediction, then to calculate that new observable, you can feed in the values of mr and lambda r. Okay, and that is how this works. So first let us calculate physical mass mp, assuming that some observations have given us what the values of mr and lambda r should be. Okay, so some observables have been observed in the experiment. Okay, they have been measured. Okay, once these observables have been measured, one feeds in some values of mr and lambda r. Okay, and try to see which values of mr and lambda r reproduce those observed results. Okay, and then you use those mr and lambda r to calculate mp. Okay, or any other observables. So that is how you should think about it. Okay, so let's calculate mp, and you know how to get this. So you look at the 2-point function. Okay, and look at the pole of it. Okay, pole of the propagator. So this is this plus this plus this. Okay, why? What we are doing here is we are writing down this 2-point function up to order lambda r. Okay, that's what we are doing. So I should have order lambda r to the 0 term and order lambda r term, but no order lambda r square term. They are not needed. So this is the order lambda r to the 0 term. Okay, there is no lambda r here. So that's the first term. Plus you have this self-energy diagram. Okay, one loop self-energy diagram. It has a factor of lambda r here, so it contributes. And this one you have seen, this vertex itself is order lambda r. Okay, so this also contributes at order lambda r. Okay, now this is finite. That's just the propagator, I over p square minus mr square plus I epsilon. Okay, so this is singular. Okay, because of the loop diagram, because it's a loop diagram, it has ultraviolet divergent. Okay, and this has this expression as we wrote before. Okay, this thing times these two propagators. Okay, so yeah. Okay, good. So remember, now whenever you are writing any Green's function, you have to always include the counter terms also that can appear up to that particular order up to which you are interested in. Okay, so this you cannot say that okay, this is the diagram, this is also a diagram that contributes, and you have to keep it. Okay, this cannot be omitted. Okay, because your action now has such terms, so they all have to be included. Okay, so let's calculate this just to be a little bit clearer. This object is now a Fourier transform of this. Okay, this is how we had looked at this 2-point function in the Fourier space, in the momentum space. Okay, so this is what I'm looking at, where the fields are having this subscript r. Okay, these are correlators of renormalized fields. Okay, so let's look at the first term. The first term in the expansion is simply I over p square minus m square plus I epsilon. Okay, this one has two factors of I over p square minus m square plus I epsilon. right? One coming from this propagator, another coming from this propagator. So you have a square of it times this integral. Okay, so let's assign a loop momentum L, and this integral is, so let me first write down the vertex. It is minus I lambda over 4 factorial mu to the 2 epsilon. Okay, that is our vertex. Okay, then I should write down the integral, the Feynman integral, which is d power 4 minus 2 epsilon d L over 2 pi 4 minus 2 epsilon into I over L square minus mr square plus I epsilon. Okay, this is because of this propagator. See, there is one propagator here, right? This, which carries momentum L. Okay, so that is what I am writing, I over L square minus m square plus I epsilon. Okay, now I should also multiply the combinatoric factor. So that's easy to find. You have here, this is this point I am drawing, this is this side, and then you have a 4-point vertex. So this one can go to any of the 4, then this one can go to any of the 3. I should have, there is nothing wrong in what I have done, but it's not very convenient. So it can go to any of the 4, it can go to any of the 3, and this can only connect this, so it is 4 times 3, and then you have 1 over n factorial, where that n depends on the order of lambda, right? And because that is 1, so it is 1 over 1 factorial. Okay, if we were at 2 loops or order lambda r square, it would have been 1 over 2 factorial. So this is the expression, and also let me now write down this one. Just a second. Okay. Now the counter term, or counter vertex, or counter diagram, better counter diagram. So this is what? Again, this has 2 propagators, which each of which carries a momentum p. So you get I over p square minus mr square plus I epsilon squared, and then you have I'm writing this vertex here, this one, I times half z phi minus 1 p square, where p square is the square of this momentum, minus half z phi zm square minus 1 mr square. Okay, now I should find out the combinatoric factor. And what is that? So let's do it here. You have again this, and then you have a 2-point vertex. Okay. These sticks coming out are from the vertex. Okay, these are not propagators, and I have to connect these propagators. So this one can go to any of these 2, this or that. Okay, let's say it goes here, 1. Then this has only one option, so which is same as this diagram, right? I'm just drawing it differently. It's the same diagram. So first one had 2 options, the second one had only one option. So you total 2. And again 1 over 1 factorial. Okay. So this is the contribution of this diagram. Okay, so So here lambda r, let's check if everything is fine. Okay, all looks good so far. Just one remark here. Look at this integral, this contribution. The integral that you have here, this one, okay, it's a bit special because it does not contain the external momentum p. Okay, so you don't see p anywhere here. But this is not a general feature. Typically, loop integrals will carry the external momenta. It is just because this loop is such that there is no external momenta that enters into it. That is why this is completely dependent of p or p square. Okay, but this is not generic. This is something very special here. So if you had a diagram of this kind, then p will also enter into the loops. Okay, and then the integral will also depend on p. Okay, so I should now do what? I should calculate this integral and substitute it in here to see what I get. Okay, so let me first do that. Integral. Let's call it I. So let's define this integral to be I. I, and it depends on what? It depends on mr square. And also on epsilon. So let me also here write mr square epsilon. This one, let's be careful and write it like this. Okay, so let's find out the loop integral. We have already done this. Let me just write the result here. Integral ddl over 2 pi to the d 1 over L square minus mr square plus I epsilon to the n is I times minus 1 to the n over 4 pi d over 2, okay, gamma of n minus d over 2 over gamma n, and then you have 1 over mr square minus I epsilon power n minus d over 2. Okay, so let's put n equal to 1. Before I do that, the integral is not really this. There is a factor of I also here, okay, because that's what comes from the propagator. So let me include that I will not write it here, I will write it outside. So this is I, capital I is this, okay, and then you have a factor of I also here. Okay, so I square gives you minus 1, capital N is 1, so there is a minus 1 here that cancels the sign which you get from I square. Okay, so you have 1 over 4 pi power 2 minus epsilon. Okay, d over 2 is 2 minus epsilon. Then you have gamma of n is 1 minus d over 2. So what is 1 minus d over 2? 1 minus d is 4 minus 2 epsilon. So 2 minus 2 epsilon, 2 minus epsilon. Okay, this is minus 1 plus epsilon. Over gamma of 1. And this one is 1 over mr square. Now you see mr square is positive. Okay, so this is a fractional power of a positive number. Okay, so there is no issue. There is no issue of knowing. There is no issue of a branch cut appearing here, and and that I should know on which side of the cut I am. Okay, so I can just drop this. If it was negative, then I have to worry. Okay, so I'll just drop that I epsilon and this will be again n minus d over 2 is minus 1 plus epsilon. Okay. Also another fact, so you have gamma of n minus d over 2, right? So because d has an epsilon, and let's say we are not taking epsilon to be integer because we want it to take any arbitrary value. So unless d is also integer such that n minus d over 2 is a negative integer, okay, the gamma is not divergent. See, gamma is analytic for all values of its arguments except for 0 and negative integers. Okay, so even though you are having a dimension d, okay, which is let's say, which will naively give you a singularity because by the power counting it appears to have more powers in the numerator than the denominator, even then it would not give a divergence. Gamma function will not be singular unless the power that you have, okay, the total power that you have, d minus n, is integer. Okay, so these are analytic functions for all non-integral values. Okay, good. So we have this here, and this I can write as I think I had already, anyway, nevertheless I should do it. So we'll use gamma z is equal to gamma z plus 1. So minus 1 plus epsilon times gamma of minus 1 plus epsilon is gamma of epsilon. Okay, so gamma of minus 1 plus epsilon is 1 over or minus 1 minus epsilon gamma of epsilon. Okay, so I will write this as 1 over 4 pi 2 minus epsilon. Is that correct? That's correct. And then you have minus sign 1 over gamma, 1 minus epsilon gamma of epsilon. Okay, and this is mr square 1 minus epsilon. Okay, so I'll massage it a little bit more. Good. Okay, so this is minus 1 over 4 pi square times mr square times mr square, this is in the denominator, sorry, times 4 pi over mr square power epsilon. Okay, and then you have gamma of epsilon over 1 minus epsilon. Okay, that's the integral, that's the value of the integral. So what is the value of that full Feynman diagram? It is this. And then yeah, so there is a factor of minus I here, there is a factor of minus 1 here, and it will combine with this factor of minus 1 here to give a plus. Okay, and then I have lambda r over 4 factorial, then you have mu square power epsilon. Okay, mu to the 2 epsilon, which is mu square power epsilon. that I will combine with, where is that, with this factor. Okay, so it will become 4 pi mu square over mr square power epsilon. Okay, that is what it will give when you combine, and then these factors. Okay, so let me write down that I should have a factor of I. Okay, so let me write and then check. So I'll get I lambda r mr square. There is a factor of half, and then you have 4 pi square, and there is factor of half. Okay, let me show you. So 4 times 3, and you have divided by 4 factorial, so that gives a factor of half. Okay, in the denominator, a factor of 2 in the denominator. So that is the factor of half here. Okay, 1 over 2. Then then I have taken care of lambda r and this factor of I. Okay, lambda r and this factor of I, and then I have pulled out a mr square from the integral. Okay, and this 4 pi square also I have already taken. Now I should write these factors, including the mu square to the epsilon. So I have 4 pi mu square over mr square power epsilon. Then you have gamma of epsilon over 1 minus epsilon, and mr square I have already taken here. So let me check. I over 2 lambda r mr square 4 pi square 4 pi mu square over mr square power epsilon, gamma epsilon over 1 minus epsilon. So that's correct. That's the correct result. Okay, now let's look at the poles explicitly. This piece here is a 1 plus epsilon times log of 4 pi mu square over mr square. Okay, plus order epsilon square term. Okay, just a second. Sorry again, it should work. Okay. So this is this factor. Then you know what gamma of 1 over 1 minus epsilon is. This is 1 plus epsilon plus order epsilon square. Okay, when I write order epsilon square, it means all the terms including epsilon square and all the terms after epsilon square also. Okay, because they are successively of lower orders. Then you have gamma of epsilon, which is 1 over epsilon minus Euler gamma, that was the number I told you earlier, plus order epsilon terms. What does that give? So in this product, the most singular term will be produced when you multiply 1 over epsilon to the 1 here and to the 1 there. Okay, when you pick out that term, 1 times 1 times 1 over epsilon, you get the most singular piece. Okay, epsilon to the minus 1. Now let's look at epsilon to the 0 term. So there are several ways in which you can generate order epsilon to the 0 term. So let's take minus gamma I here, which is order epsilon to the 0, multiply it with 1 here, okay, and that one there. So that gives you minus gamma I. Okay. Also, if you what happened? Yeah. So that is one source. If you multiply this 1 over epsilon with this epsilon, okay, the pole term, multiplying the order epsilon term gives a finite value, finite term, right? So this also, that is why one has to be very careful in getting the finite results. See, getting singular part is fine. You can just drop all the order epsilon terms. There is no problem. But if you want to have the finite parts also correct, you have to expand sufficiently in the orders of epsilon, depending on up to what loop you are working. So at one loop, this will be sufficient. So 1 by epsilon times epsilon gives you 1. So that's plus 1. Okay. Then also when you multiply this 1 over epsilon term with this epsilon term here, so 1 over epsilon, 1 from here, and epsilon term here, that also gives you a finite piece, and which is log of 4 pi mu square over mr square. Okay. This is fine. And did I miss something? 1 over epsilon, order gamma, mu square plus 1. This is perfectly fine. So I will just bring it a little closer. This is what you get. Okay. Plus order epsilon terms. I don't worry about order epsilon, because now when I take epsilon going to 0, this will drop out, and I have kept correctly all the finite terms. Okay. I will rewrite it a little bit differently. I will write it as 1 over epsilon plus log of 4 pi. So that is log of 4 pi coming from here, minus Euler gamma, that is here, this term, plus 1 plus log of mu square over mr square plus order epsilon. Okay, so that's the result for this. Now, when I add this, I think it will be better if I write it again here. So this piece what is that? Yeah, I lambda r over this vector. Let me write it. So let me change this. So 4 pi square is 16 pi square, and there is a factor of 2 here, that makes it 32. Okay, so 32 pi square. Okay, good. So that factor is there, and then we have all these poles. 1 over times 1 over epsilon plus log 4 pi minus Euler gamma plus log of mu square over mr square plus order epsilon terms. Let's check. Did I miss? No, did not. Yes, I did miss 1. Okay, plus 1. Okay, and then I should add to this the counter term and of course the pure propagator term also. And this was this one. The counter term provides you this. What are the factors? I'll write it here. Half z phi minus 1 p square. Okay. Minus half z phi zm square minus 1 times mr square. Okay, so now I have the sum of these two is equal to the sum of these two expressions on the top. Okay. Now I want the following. I want the sum to be finite. Okay, because if the sum is finite, then the mass which I am going to calculate at one loop up to order lambda r square, okay, the physical mass, that will be finite. Okay, so first let me make the sum finite here. Okay, that's what is called renormalization. So I'm going to subtract infinities now. Okay, so let's look at this term. This is what you had gotten if you had not split the Lagrangian the way we have, okay, and just continued with the parameters lambda and m. If you had continued with the bare parameters lambda and m and bare field phi, this is what you would have obtained. The only difference would be that instead of lambda r and mr, you would have lambda and m. Okay. But even after that you have used lambda r and mr, nothing has changed because it's still the same integral. Instead of lambda you have lambda r, instead of m you have mr. Okay. But the advantage is now that you have also this term. But in this term, the z phi's and zm's are still at our disposal. There is nothing that fixes what z phi should be and zm should be. Okay. In the steps that we have done, there is nothing telling you what is the value of z phi and what is the value of zm. Okay, so what we can do is we can choose the values of z phi and zm such that they cancel the singularities that are present in this expression in the loop diagram. Okay, so what I should do is to make this finite, I make the following choice. First, let's look at if there is any singularity in this loop diagram which is proportional to p square. Okay, because there is a term proportional to p square in the counter term which can take away any singularity which is present here that is proportional to p square, but there is none. Okay, there is no term that is proportional to p square. Okay, so there is no such singularity that needs to be cancelled. Okay, see this p square term cannot interfere with this term. Okay, because you keep mr fixed, that's value you have chosen, so you can fix the value of mr. Okay, and then p can be varied, right? You can look at the 2-point function for different values of p. Okay, so changing that p will change the value, but this one will not change. So any singularity that is proportional to p square here, okay, cannot be utilized to cancel something which is independent of p square here. Okay, so we can make the following choice. We can choose z phi to be equal to 1. Okay, so if z phi is equal to 1, this goes away and that is fine. I don't need any such term to cancel any poles here. So that's a choice I can make, and it's good. Z phi doesn't. So to this order, the field phi is equal to phi r, right? Because we had all these z's always start with 1. Okay, so to order lambda r, phi is same as phi r. Okay, but this will change if you go to second order. Okay, when you have different other diagrams at 2 loops, this statement will change, but up to order lambda r, phi has remained phi r. Okay, or phi r is same as phi. The normalization has not changed. Okay, now let's look at this term. This is proportional to mr square. You have an mr square here, so I can kill this singularity. Okay, so for that I can choose. We can choose z phi to be 1 and lambda r. There is a issue of factor of I. How come? Yeah, because I missed the factor of I here. This comes with this counter vertex as a factor of I. Here, this one. That is what I had missed. Okay, so lambda r mr square over 32 over 32 pi square. This is this factor. I have, see, this is common in both. The I factor is common in both, and I am now looking at this part. Mr square minus, because you are adding these two up, minus, so this one gives you half, minus half, z phi zm square minus 1 mr square. So when you add these two up, you get one term which is this, and I want this to be finite. Okay, I am not specifying what exactly finite number I want to be, but I want it to be something finite. No, there is a pole that I have missed. This 1 over epsilon I have missed. Okay, so now if you choose, so this is finite, so now we can choose zm square to be 1 plus lambda r 4 pi square. Okay, if I make that choice, let's see what happens. See, z phi is already equal to 1 plus something of order lambda r. Okay, so z phi is, because we are doing everything correct to order lambda r only, I have z equal to 1. So z is 1. Okay, and if you compare, then the sum of these two should be 0. So zm square should be equal to 1 plus 1 over epsilon lambda r over 4 pi r square, 4 pi square. Okay, m square cancels, and this factor of half divided from 32 gives you 16, which is 4 pi square. Okay, 16 times pi square is 4 pi square. So that is what you get. And if you do this, then this makes the sum finite. Okay, so here's the summary. Let me write it again. Oops. So summary of what we have done is the following. We took this one loop diagram, plus took the counter term, and we made this finite. Okay, and to make this finite, we have seen that we can take z phi to be 1 plus something at order lambda r square. Okay, so the term which is proportional to lambda r turned out to be 0. So 0 times lambda r plus order lambda r square. Okay, so it is really 1. That is z phi is equal to 1. Okay, it's a very special thing that has happened, that the lambda r term is vanishing. Okay, it will not be true in general, but in some cases certain terms might just vanish. Okay, for whatever reasons, but they can vanish. Okay, it's not necessary that each term has to be non-zero. Okay, so z phi is 1 plus order lambda r square, and zm square, I have found that it should be 1 plus 1 over epsilon lambda r over 16 pi square. Okay, plus order lambda r square. So if I make these choices, make this plus this finite. Okay, now you see, you can take epsilon going to infinity limit. Because when you take epsilon going to infinity limit, these z's, they become infinite. You see, this z phi doesn't become at one loop, because this is 0. But in principle, if you were to calculate 2 order lambda r square and other terms, okay, they will diverge. Okay, but and also Zm has diverged. So what has happened is that the bare mass M, which was written in terms of the renormalized mass as Zm times Mr, okay, this has become singular. The bare mass is singular or infinite in epsilon going to 0 limit. Okay, because Zm becomes infinite, but Mr is Zm becomes infinite, but Mr is something finite. We have fixed Mr. We have said, okay, Mr takes some finite value, whatever value you wish to choose. Okay, the cost of making Mr finite is that the bare parameter becomes infinite because Zm is finite. But I am fine with that, because if I look at this sum, which is what really enters into the calculation of physical mass, which is something observable, okay, that is finite. So I am going to get finite results for physical observables, but the bare parameters and bare fields are going to become infinite. So your action or Lagrangian density is going to become infinite, but you are still going to get finite results. Okay, so this is what is the renormalization program. We make the bare quantities which are unphysical, non-observable objects. We make them infinite, and we still get predictive power because the observables become finite, because they are expressed not in terms of bare parameters and bare fields, and not in terms of bare parameters Mr and lambda r, but they are expressed in terms of finite parameters lambda r and Mr. But remember, these are also not physical observables, lambda r and Mr. Physical observable is something like physical mass MP. Okay, that can be expressed in lambda r and Mr. Let me show you exactly what you will get if you calculate the physical mass. Okay, but before that, let me make these remarks. So in epsilon going to 0 limit, that is d equal to 4 dimensions, your physical world. Okay, the bare coupling constant, okay, in this case you are just seeing Zm, so let me make statement only about that. The bare mass parameter M becomes infinite. Okay, which means that your Lagrangian density also becomes infinite. Okay, but still we get finite physical mass. Okay, so this is nice. Let's see how to get the physical mass. It's almost there. So we want to get physical mass correct up to order lambda r. Remember, we are doing perturbation theory, so you will be able to calculate observables up to some fixed order in the coupling constant, which is your expansion parameter. So what do you get? You get the following. This loop diagram plus the counter term after cancelling everything is I over p square minus m square plus I epsilon square. This is coming from the two external legs, okay, times the remaining part, which is I lambda r over 32 pi square, okay, 32 pi square, then mr square times 1 plus log of mu square over mr square plus log of 4 pi minus Euler gamma plus order lambda r square terms. So I'll drop them, or maybe just write it like this. Okay, that's your finite result for this object, this sum. So how do you get the physical mass? We have seen earlier that we should look at the pole of the 2-point function, and this has the form I times the residue, okay, divided by okay, I should have first drawn the diagrams. So this is this propagator, the lowest order contribution, plus all 1 pi diagrams, okay, one particle irreducible. You remember this, we have discussed about this earlier, okay, plus okay, it has stopped working now. I'm finding it difficult to write. Okay, so this and of course all other such diagrams, and here this is equal to, how should I write, where this one particle irreducible, this doesn't contain the legs, okay. Let me put these vertical arrows to say that you don't have to include these propagators, okay. These are amputated ones. So for amputated object I will write this, or simply even I can remove that. We had defined this earlier as minus I sigma p square, okay. It will be a function of the scalar p square, and with this it becomes I times the residue over p square minus mr square minus sigma of p square, okay. It also depends on mr square, and of course lambda plus epsilon, okay. and of course other terms which are, that's the structure, which are not singular. Okay, so that's the 2-point function, and what you have here is really this object, right? 1 pi. So this sum is 1 pi up to order lambda r. So this 1 pi up to order lambda r is I times, see, if I remove the propagators, meaning I remove these square, then whatever is left is I sigma. Okay, so this is how should I write? Okay, I sigma. So because there is a factor of I already, so whatever is left here is sigma. So sigma is sigma p square up to order lambda square is 1 lambda r mr square over 32 pi square times 1 plus log of mu square over mr square plus log of 4 pi minus order gamma. Okay, this is correct up to order lambda. So you see what the physical mass is. Physical mass is mp is equal to or mp square is equal to mr square. See, this is the pole, right? This is the physical mass. Okay, mr okay, maybe I will stop here. It is becoming difficult to write. So you can calculate the physical mass here. Okay, and we have the finite result, and you see that the result depends on mu, as I was saying earlier, that the result will depend on mu, even though you know that it should not. Okay, but that's an artifact of doing a perturbation theory, because you have stopped at some order, there is a mu dependence, and then you also get these constants. Okay, so these are also part of your result. These are all order lambda r terms, but here maybe I'll tell more in the next video, but I'll just say in words instead of writing. Here, yes, here, when we were subtracting infinities, we were choosing what the value of Zm should be. Okay, we chose to subtract only the pole terms. Okay, we chose Zm such that only 1 over epsilon gets removed. Okay, because that did the job of making the sum finite. But to get a finite result, you have freedom to also subtract some finite pieces, right? So in addition to this 1 over epsilon, if you were to remove the log 4 pi and this gamma minus gamma, Euler gamma also, you still get a finite result. And you have that freedom, right? No one can tell you that you are not allowed to subtract this. Okay, you are allowed to, because that additional subtraction is also going to give you a finite result. Okay, this is what is called a renormalization scheme. Okay, how much finite pieces you subtract is a particular choice of a scheme. Okay, I will write in these things in next video because my pen is not writing now, and we'll talk about a little more about these things in the next video.